So thanks for staying here that late, and welcome to my talk about the low-cost fluorescent quenching detection system that I'll present you right now. I am mainly working at the Light Technology Institute, but part of my working group are also located at the Innovation Lab and at the Institute of Microstructure Technology in Karlsruher. So let's come to the motivation why we are interested in fluorescence quenching or detection of nitroaromatic compounds in general. There's a huge demand for security at airports and custom controls, and which is actually carried out by a sniffer dog, which is the gold standard for detecting explosives or drugs at the airport. But this is very costly and ineffective because he can only work 20 minutes in a row and then he needs to rest. And it needs a lot of training. He needs a person that permanently takes care of it. So this is one of the reasons why we developed in last time fluorescence quenching detector for gases, so in the vapor phase. So there are definitely a lot of applications in smart home for sensing of the ambient air. There is a potential thing with healthcare that you can detect cancer, for example, or other diseases. And well, yesterday we had this beautiful whiskey tasting, and recently a colleague of mine published a material that is able to distinguish different whiskeys, also based on fluorescence quenching. And for sure that if we want to go into water or into the liquid phase, then in Germany we have some problems with unexploded ordnance that needs to be detected or cleared from chemicals. And now that not everybody seems to be familiar with fluorescent quenching, I'll slightly introduce how fluorescent quenching is working. So the principal setup is relatively easy. We'll have a UV light source. We have our sample that is excited by the UV light and emits light, and then we'll have a detector. In this case, we'll have a spectrometer. You can also use a simple photodiode, or what we later on will use is a CCD camera. And starting with the measurement, you will have an initial intensity, and as long as there's no quencher present, the intensity remains constant. As soon as you inject the vapor into the chamber, the intensity is going down, and later on, if you flush the chamber with fresh air, the intensity was going up and is able to recover partly. And the physical principle that is underlying is that you have a photoelectron transfer, which means what happens in these fluorescent dyes is, well, typically you have in organics you call this a HOMO and a LUMO level, which is comparable to the valence band and the conductive band in a semiconductor. So you excite the electron, and in if the quencher is present, the electron can move to the LUMO level of the quencher and decay without any radiation. That's the reason why the fluorescence intensity will be decreased. And this technology offers potentially the advantage that it's ultra-sensitive and well, you only need a very few components, so you can make it very low cost and portable at the end of the day. And the fabrication of our chips will be done in a row-to-row manner. So we have a hot embossing tool based on a row-to-row fabrication scheme. So we have a master structure for the microfluidic channel that we'll imprint into the polystyrene foil. So we'll heat the whole thing up to above the glass transition temperature of the polystyrene, and then squeeze it through, apply a certain pressure, and we'll end up with having these microfluidic channels with an inlet and an outlet and a test chamber where we can print different things in the middle into that. And how we do the printing will then be done with an aerosol jet, which offers the advantages. First of all, it's a digital printing technique. It is contact free,
which is especially beneficial if you want to print on a previously structured substrate, and it's additive, so you can add different layers on top, which we don't need in our case, but the technology works as follows. You have the ink in an ultrasonic bath, and it's called atomizer because the company is calling this an atomizer. And then you'll apply an ultrasonic, you generate a kind of a mist in these tiny droplets or aerosols, which then be carried by a nitrogen carrier gas into the nozzle. And in the nozzle, it will be mantled with a sheet gas, and then you'll have a really tiny stream of these aerosol particles that can be deposited in any kind of manner that you want on the substrate. And recently we could print different materials, so nanoparticular polymers or even mixtures of both to print fully flexible and printed photodiodes. And again, we also printed these fluorescence quenching arrays for nitroaromatic compound detection, where we could go down to a detection limit of 1 part per billion. And in our case, then we functionalized the microfluidic channel. In this case, you'd see the fluorescence image of this, and so therefore the walls of the fluidic channel are not visible. And with the Aerosol Jet technique, and by measuring a cross-section of this, you'll see that unfortunately we have the problem that we slightly dissolved the polystyrene from the bath. So there is usually, this would be the top surface of the polystyrene, and within these spots you see that it's dissolved. So the problem was simply that there was a little bit too much of a solvent within the ink when it hits the substrate, which dissolves this, and then you have something like a coffee staining effect, which you probably know. If you take a drop of coffee, put it on your desk, and it dries, then you have this dark ring on the outside, and this is due to the different drying and the different concentration of the material within the solvent, and then you have these mahogany tracks that cause the diffusion to the edge. And this is what happens here, and unfortunately, additionally, we dissolved the material from out there. So what we ended up having here is not the pure material, it seems to be a mixture of the polystyrene and the fluorescent dyes. And finally, the final step to manufacture our device is then a thermal bonding. We can use the same tool that we use for the imprinting in advance. Just leave out the master structure and take 2 sheets, the previously imprinted and print with the printed structures, and the polystyrene sheet to cover it. And so we end up with the microfluidic chips at the end of the day. The system that we use to measure all these things is, you see here the schematics. So we have in principle the UV LED, some optics, a dichromatic mirror, a sample holder that can hold these microfluidic chips that can hold some small layers, or any other kind of samples that we want to use later on. Here you see it in real space, so it's not really big, but you see there's a lot of space to what you can optimize the size to make it even more portable than it is right at the moment. Okay, and so to decide which kind of materials we would like to use for the fluorescence quenching array, as we had a lot of experience with these materials for organic materials in building OLEDs and organic lasers, we started with these ones, and we started in a liquid phase. So the first thing that we've done is a look at the absorption and emission characteristic to figure out if there's really the photoelectron transfer, or if there's first resonant energy transfer within the material. So, but usually within these materials, the absorption and emission is separated enough, or at least the emission of these materials is far enough away from the absorption of the quencher that we'll use later on, so that there is no energy transfer. To see if this is working or will work in principle, you'll need to measure the HOMOs and the LUMO level of the different materials. So in this case, we use the materials which is called polymer white, polymer blue, polymer green, or PFO, and the first ones are PPV-based materials from Merck, which change in the side group, which have a slight change in the side groups, which make them emit white, blue, or green, and the PFO materials. And here are the analytes that we are aiming for. This is nitrobenzene, dinitrobenzene, or dinitrotoluene. And there you can see the HOMO and LUMO level of these materials, and you see that you have a possible energy transfer. And what else did we observe? We could also prove that there is no shift in the emission of all these materials, which is also important. So then we measured in toluene, and based on toluene for different concentrations, we could figure out that this will in principle work completely in solution. Then we did a linear discrimination analysis to see if we can later on also discriminate in between these materials. So this also works out. And then we went over to water. We spin coated the polymers onto a glass substrate and could measure the lifetime within water, and to see that we have a dynamic quenching process. So this is also, some of them are even below the detection limit of the measurement system, but in principle we could prove that we have the dynamic quenching. And then we went into the microfluidics and measured the whole thing, and one of these measuring examples you see here, the first thing was we measure in air, we filled it with a liquid, continuously increased the amount of quencher that is within the water, and then applied a linear discriminant analysis to differentiate between. And here we have the following problem, that all of these single arrays did not work perfectly, because some of them, you remember maybe this image, then some of them have a really high sidewall, and some of them are blocked by air bubbles, because when you go from one solution to another with a different concentration of the quencher, there might be air bubbles and they are blocked. So if we take them out of the analysis, then we could end up with a discrimination that has a probability of more than 95%. Even so, they are close together. If you observe them in a three-dimensional space, you would see that there's different branches going up and down. So, to conclude, well, I introduced a relatively portable system that is able to detect fluorescence quenching. I showed you the manufacturing scheme, which is in principle row-to-row fabrication, or that enables row-to-row fabrication in the future. And we could also prove that these more or less first arrays are able to discriminate these different concentrations. And what's up to come next? So we will try to integrate all this into our row-to-row device to bring this really into a one single manufacturing step. We will definitely have to optimize a little bit of the ink to get rid of these coffee staining effects. And for sure then we will have to work on a pattern recognition algorithm to differentiate different materials. With this, I'd like to thank you for your attention, and thanks to the colleagues that contributed to this work.